Hello everybody and welcome back to Elementary Statistics Online at Frederick Community College. In this video, I will solve a problem that deals with goodness of fit testing, and I will use a TI-83 calculator to show you how to do the computations. So if you're using the TI-84 calculator, you won't have to do all the steps that you will see in this video, but conceptually, this is a still good video for you guys to watch. If you have a TI-83 calculator, this is definitely going to be very helpful because there is no built-in function that will do goodness of fit problems for you if you have a TI-83. So we need to know what to do if you have this type of calculator. Don't worry, it's not too complicated, just a couple extra steps. So let's go ahead and take a look at the following problem. I will solve a problem from your homework. Chapter 11, problem 4. You might have slightly different numbers, but the setup should be the same. So let's take a look at this problem. We're interested to see if phone calls are equally likely to occur any day of the week. And we have a sample of 672 randomly selected phone calls and also when these phone calls happened. So we have a frequency table telling us the following information. Okay, so let's go ahead and fill out all of these parts. And as I go, I'm going to also pretend that I'm submitting this by hand. Okay, so if this is a paper pencil assignment, how would I do it? Okay, so let's see. A phone call is equally likely to occur any day of the week. We want to see if that is the case. So the null hypothesis will always say that our frequencies, our observed frequencies, follow some sort of distribution. In our case, we want to see if phone calls are equally likely to occur on any day of the week. Okay, in other words, the proportion of phone calls on, let's say, Monday is the same as Tuesday, is the same as Wednesday, and so forth, all the way up until Sunday. They're all the same. So P's here represent proportions of phone calls that happen on that particular day. Okay, so the null hypothesis will always say our expected values, our observed values do follow a certain distribution. Okay, and then the alternative hypothesis will say no, they don't. So in this case, we say no, they're not equally likely to happen, which means the proportions are not all the same. It's not necessarily to find out what the actual proportions are. We're just saying that no, they're not all the same. Okay, and we're going to be using goodness of fit test because this is literally what we're trying to do. We're going to see how well our observed values fit our expected values. Okay, so let me highlight our test. That is our goodness of fit test. Okay, so let's go back to our problems and let's see what's going on here. We have 672 phone calls, and if they are equally likely to happen, that means on each day we should get how many? Well, 672 divided by 7 is 96. Okay, so I'm going to plug in 96 in each one of the cells here. Okay, and B is goodness of fit. All right, now what am I trying to see? I'm trying to see if the phone calls are uniformly distributed, right? That is exactly the same as saying all the proportions are the same. So for this one, for the null hypothesis, I would choose the distribution of phone calls is uniform over the days of the week. The alternative hypothesis will say they're not uniform, so I select these two options. Okay. All right. As far as computations go, what I'm going to do now, just to save a little bit of time, I've already done it. Let's go to your columns, and in L1, I plugged in all of my observed values. and in L2 expected. Okay, and let's see what's going on here. So some days we have a pretty close number as far as the expected, right? So we got 95, expected 96. Others a little bit more, 110, expected 96. Here it's a little less, 90, but expected 96. So overall, we're trying to see if these differences are significant. If overall our differences are too much, okay? Are they all different? Yes. Actually, we never got 96 phone calls, right? Not in a single day. But are they different enough? That's what we're trying to figure it out in here, okay? So how do we compute the test statistic? That is the next question, right? Well, actually, no. The next question says the degrees of freedom. In this case, we would say 6. And how do we know? It is the number of categories in our data set, okay, minus 1. So we had 7 categories, minus 1. We have 6 degrees of freedom. So the test statistics for this data. If you had a TI-84 calculator, you would go to Stat, Test, you would scroll down, and right next to this chi-square test, you would have chi-square goodness of fit. You plug in your L1, L2, compute, boom, you get your answers done. Unfortunately, that's not the case for TI-83 calculator, but that's completely fine. We still have a way to solve our problem, okay? So what we're going to do, we're going to follow the following rule, okay? We need to compute this this quantity right here. It's the summation of observed minus expected squared divided by expected, okay? And we're not going to have to do it by hand. The calculator will tell us how to do it. So I'm going to open parentheses and say observed, which is L1, minus expected, which is L2, close the parentheses, squared, divide by expected, which is L2, and these values I'm going to store. That's what this button stands for, STO. We're going to store them in L3. Okay? So now if you go back to your columns, you see that you have these numbers over here for each of the category. Okay? That's what we got over here. We're not done. We need to sum them up. So go to second, stat, scroll to math, select command 5. We're going to sum up values in the column L3. Okay, so 14.1458. 14.1458. That is our test statistics. 1458. Yeah. Okay. Let's go ahead and plug it in our homework assignment here. 14.1458. Okay. They want 3 decimal places. All right. They want 3 decimal places, so this becomes 6. Okay. So that's how you compute your t-statistics. What about p-value? That one, we're going to do the following. We're going to go second, variables. And we're going to select command 7, chi-square cumulative distribution function. That's what this stands for, 7. And the syntax here goes like this. Remember, chi-square tests are always right tail. So your lower limit in this case is whatever your test statistic is, right? So we're going to say 14.14583333. And I'm just trying to be as accurate as possible. We're going up to infinity, right? So let's say 100,000. That should do it. And then the last parameter that you need to use is degrees of freedom. So it's 6 in our case, not 60, 6. Okay, so here's your syntax. Test statistics goes first. large number, you can do 1 E99 or 10 to 25th power, whatever you want to do. This is big enough. And then degrees of freedom. Okay, so we compute this value right here, 0.028. They want they want 4 decimal places. Okay, that's still 0.028. Okay, let's put it here as well. 0.28. And let's take a look. What is our alpha? Alpha is 0.05. So 0.028 is less than alpha level, which means we have significant evidence to reject the null hypothesis, right? So there is sufficient evidence to conclude that the funcals are not uniform, right? So let's see where that is. There is sufficient evidence to conclude that distribution of funcals is not uniform. So that would be this option right here. Okay, and let's see if that gives us the right answer. Let's just double check everything. Okay, what am I missing? Nope, let's go ahead and, oh, here we go. Based on this, we should reject the null hypothesis. That's right. Okay, we'll reject the null. There is sufficient evidence to conclude that the distribution of funcals is not uniform. It's thinking. Yep, we're good. Okay, so everything is right. So over here, what would I do? This is less than 0.05. Okay, reject H null. We have sufficient evidence to conclude that funcals are not equally likely to occur on any day of the week, right? Okay. We reject this statement right here. We reject this one. Okay, if you want to go ahead and cross it over. We reject this one. We have sufficient evidence to support this hypothesis right here. Okay, so let's say you're writing your solution on a test. This is all I expect to see. Your null and alternative hypothesis need to be in the context of the problem. Okay, then here's your test statistics. P-value. P-value tells us what to do. If p-value is small, smaller than alpha level, we reject the null hypothesis. Okay, there is sufficient evidence to support the alternative hypothesis. If p-value is large, bigger than alpha level, we fail to reject. Okay, but this problem basically says what? This solution says what? Well, some days you can expect to get more funcals than others. Let's see which ones. Looks like Friday and Saturdays you get more, and looks like Thursday really you don't get as many. So these are the days, and also Tuesday, where we get the most difference as far as the expected and the observed values go. All right, so that's what you would have to do to compute t-statistic and p-value on a calculator that doesn't have the built-in command. A little more steps, sure, but is it worth it to buy a new calculator? I don't know. I'm gonna let you decide. All right, well, thank you for watching. I hope this was helpful.